Welcome to a lesson with Dr. Powell. In this video, we're going to do some practice with taking limits. So you can look at the problem, practice it on your own, and then, after you pause the video, pause the video first after you see it, and then have the video go again to check your solution and how it's working. All right. So this is going to be problem, this is going to be problem number 1 here. Let me just get that going here. So problem number 1. This is going to be number 2. All right. So both of these limits have something to do with infinity, and we'll see that as we go along. Okay, so this first limit deals with this fraction. And if you haven't started already, go for it. So pause the video now, and then I'll present it. Okay, here is the solution for problem number 1. Now, as a limit, basically what we're doing is we're going to be looking at equivalent fractions so we can, until it's well defined, to plug something in. I mean, like right now, if you will, plugging in infinity is not really a concept unless you do a kind of an infinite squashing, which I have in some of my videos. So, if you think about it, if you like plugging in infinity, like on the bottom, you're going to get something infinite, and it will be well defined. Notice, because the fourth power, something negative, the fourth is going to be positive. This is going to be really big positive. These guys are going to be really small because 4 over big, 4 over big. That's going to be basically 0. So basically you're going to get something well defined, but it's going to be infinite. On the top as well, you'll get something defined, and it will be infinite. Basically, it'll be like some kind of infinity over infinity, but that's not enough, because things like that don't really cancel, because there's lots of ways to go to infinity over infinity along the way, and we need some kind of algebraic manipulation to help us. So we're going to be looking at equivalent fractions until when we plug in negative infinity, if you like, or take a limit, it's going to be easy to see what it is. Because right now, if you're just looking at a form infinity over infinity, that's not good enough. That's not well defined, because there's lots of ways of getting infinity over infinity. Here's an example. 3x over x is one way of getting infinity over infinity, but this will limit to 3. Because all along the way, the numbers will cancel here that you're plugging in. You always have 3, and the limit will be 3. But notice how you could change that. That 3 could have been a 5 or something else. So a limit form of infinity, therefore, is not well defined. You cannot cancel things like that. So don't try, please. So we're going to look for an algebraically equivalent fraction that'll make this more clear. We can multiply or divide the top and bottom by the same thing. Now, I'm noticing that like a square root of x to the 4th is a lot like an x squared. If I were to divide out, that's a leading term, by 1 over x squared, so I divide by x squared on top and bottom, let's see what happens. Now on the bottom, it's the same thing as doing something like this, right? This is equivalent to that, especially if, x is going to negative infinity, but it's going to be positive, and then square root. It's going to be positive square root there. That's going to be okay. Now, the nice thing about this square root is this part right here can actually hop inside this square root and distribute to all those guys. This guy will distribute into all of those. So when it does, on the top, we'll end up getting 5 plus 4 over x to the 4th minus 5 over x squared. Now on the bottom, and that's a 4, if you can see it right. Okay, on the bottom, let's see, we're going to get square root of, that's going to come through, that'll be 9 minus 4 over x to the 5th plus 4 over x to the 6th. Okay, now taking a look at this, is this a good equivalent fraction where it makes more sense to plug in negative infinity? Notice that that it is, because like 4 over infinite, that's going to go to 0. This guy will also go to 0. This guy will go to 0, and this one will also go to 0. You'll be left with 5 over the square root of 9, which is 3. 5 over 3. That'll be the limit there. That's the solution. Now, in showing work, technically speaking, I mean, a lot of problems might, it's best to show how the limit distributes after you do this. I mean, we could have, if you wanted to, notice how we introduced this fraction here. So if we wanted to really show work, what we could do is we could say, okay, I know that the limit of this right here, the limit as x approaches negative infinity of this guy right here is 1, because things will cancel nicely. So this is just another way of saying multiplication by 1. You can multiply anything by 1. So I'm going to multiply this whole limit by 1. Now the nice thing about limits is I have this limit, and then I also have a limit right here, x approaches negative infinity, and then I have the whole bit. I won't rewrite it, but just the same thing as I had originally. Now notice limits distribute and undistribute across multiplication. So really, so I have a limit of something times limit of something. Well, both of these limits can kind of combine and come out. That's a property of limits distributing over multiplication continuous operations, as long as it's well defined in such a with the things we're inputting here and here. So really the limit can pop out. So really that could be a step in your explanation to explain that. So that's how we could even get to that point. Now next, notice at this point I'm doing arrow here, arrow here, arrow here, arrow here. Well, really what I've done is I've taken the limit and I've hopped it across the division symbol, because limits distribute across continuous operations, so they can go into or inside of continuous operations, and division is one of them. It's kind of like a 2-input one, but it works. So the limit can come down here, and it can come up here. And then the limit further can go across cut across addition and subtraction, so it can pop on to each guy right here and here. And then if we just use our notion that we know what that limit is and that limit is, we're set to go on those. Now how does this limit bump into the square root? Well, square root is a continuous operation. It'll hop onto the inside, so you can go to each one. So include something like that in your explanation if you really want to make sure you're showing enough work, steps, and detail. Okay, so that was the solution in its entirety and with an explanation for problem 1. Okay, so let's just get rid of some of this stuff right here. So, all right, and we know the solution is, okay, so the solution is 5/3. Maybe I'll draw that again. Okay, so that's problem number 1. Let's, now we're going to look at problem number 2. All right, so there's your limit. All right, go for it. Okay, now here's the solution. Let's take a look at this right now. So, if I go ahead and just think about, a plugin, see if that even makes any sense here. Just for kicks, just think of what this even means. Now, on the bottom right here, what's 2 plus something to the left of -2? So on the number line, -2 is right here. Something to the left is going to be more negative. It's going to be just a little small negative number, it's going to be 0 minus. So you could actually replace this with 0 minus on the bottom. Now on the top, so you can have -2 and -2. That's going to be like -4. It's going to be like -4 minus, if you will. However, basically that's just -4. You're heading toward -4 on the top. So it's -4 over a 0 minus. Now you could see this negative and this negative. Like the bottom's like negative, the top's negative. Those negatives cancel. This is really the same thing as like +4 over 0 plus. And you think about 4 over 0 plus, what is that going to be? So 4 over a very small positive number is going to be positive infinity. Now, this kind of terse notation with plugging in actually has a limit meaning. I mean, when I write in 0 minus here, really what I'm saying is, I mean, I could interpret the fraction I wrote like right there as negative 4x limit as x approaches 0 from the left side. It's really a limit statement. It looks like a plug-in, and ideally, if you want to think about filling in holes and redefining functions to include infinities and stuff like that as acceptable outputs, it really could be interpreted as a plug-in as long as you're dealing with things that are left continuous or right continuous with the plug-in in your definitions. I mean, there's enough definitions you could swap around, so it would be acceptable to think about a plug-in even in a rigorous sense. But so what we'd end up getting here, but this is the limit, positive infinity. Now, if this idea wasn't too clear to you, you could always just plug in numbers that are a little bit to the left of negative 2, like negative 2.1 plus 2 and negative 2.1 minus 2. And in the calculation of this, notice on the bottom you're going to get like a negative 0.1. On the top you have like a negative 4.1, and so that's going to be positive positive. You're dividing 4.1 by 0.1, which is the same thing as multiplication by 10, so it becomes 41, which is a lot larger than what we had before. And as you keep on doing numbers that are closer and closer to negative 2 on the left side, you'll notice you're going to get bigger and bigger positive numbers, and then you can deduce that it'll be positive infinity. But if you want kind of a nice logical argument just to get cut to the chase, this is one you could use for your explanation. Okay, thanks for watching.